Okay, everybody, welcome back. We are continuing our Chapter 9 notes on atmosphere and severe storms. And we've gotten through sections 1 through 3, and we're starting on section 4, the actual weather processes themselves that contribute to these storms and different atmospheric hazards. There's going to be 4 main points in this section, section 4, regarding the atmosphere. And those are these 4 right here. First of all, we're going to talk about pressure, what atmospheric pressure is, and how differences in pressure cause wind to move from point A to point B. We're also going to be talking about vertical stability of the atmosphere. What that means is if air is unstable, it's prone to rise. All right, and so is air going to stay where it is, or is it going to want to rise up? We're going to see how rising air contributes to the storms that we're going to be studying. Thirdly, we're going to mention the Coriolis effect. Coriolis effect is an effect due to Earth's rotation that causes fluids to swirl one way or the other. And this definitely affects some of the air patterns and circulation patterns around the world in the atmosphere. And fourthly, we're going to talk about how different air masses interact and slam into each other. You can have cold, dry air masses. You can have warm, humid air masses. And their difference causes them to not mix very well, but causes them to hit each other almost like different armies. So we're going to start with atmospheric pressure. Let's go ahead and get started. So atmospheric pressure is really just the weight of air above you, like a column of air. Think about something that has your footprint or is the size of your body from above. The air above your body, all the way up into the top of the atmosphere into outer space, actually has pressure. It's being pulled down by gravity, and your body has to withstand that. Now, you don't feel like you're holding up all that air right there. So let's pretend this is you right here. I'm going to just draw a stick figure, all right? And all the air above your head to outer space is pushing down on you. All the air molecules all the way up to space, hundreds and hundreds of miles up. All right, well, you don't feel that. Well, you do, but I'll tell you, you would definitely feel it if that pressure were not there. What all of this air is doing is it's exerting about 14.7 pounds, and it's like pounds of force, per square inch on every square inch of your body. Almost 15 pounds of force. This right here that I'm drawing, at least, it's about a square inch. It may be different on your screen, of course, but a square inch is maybe a little bit bigger than a quarter. All right. Your body would definitely detect if this pressure were not here, because you're used to pushing back because this pressure is pushing down on you and on every square inch of your body, and your body's pushing back, and you reach equilibrium and you feel comfortable. But I'll tell you what, if this pressure were taken away, what would happen? Well, your body is used to pushing out, and so you would swell up into a big balloon, and probably horrible things would happen to you because your body is pushing out. So you don't feel it, but that pressure is still there. We measure things in pounds per square inch, or PSI. We also measure barometric pressure in what's called millibars. On average, well, not on average, but roughly, you experience about 1,000 millibars of pressure at sea level. So these are, you might say, equivalent values, just different units. All right, so the air is pulled down because of gravity, and that's what you feel as pressure. And as you go up through the atmosphere, pressure is going to decrease, right? Because as you go up, you're getting above a lot of those air molecules, and so there's less air above your head, and so you're going to feel less pressure. So not only does the pressure decrease, but density increases as well. Think about this for a second. If you have a column of air, all right, so here's a column of air right here. So the bottom is Earth's surface, and the rest of it, all that air goes up into outer space. The air at the bottom is feeling more pressure, so it's going to be squeezed together more. All right, but as you go up, there's less pressure above, so they're less squeezed together. And as we go up, there's even less and less and less pressure. So most of the density of the atmosphere is really at the very bottom, because that's where it's squeezed the most. So pressure gets less and density gets less as you go up through the atmosphere. Take a look at this next diagram. It may help you. All right, so kind of like I just drew right here, most of the weight is at the bottom. So the air molecules are squished together. You can squeeze a gas together. You can compress it. You can't compress a liquid. You can't compress a solid, but you can compress a gas. So these are all compressed at the bottom because of all the weight from above. But as you go up, there is less weight and there's less squeezing. So the air molecules get much and much further apart. This is a graph right here, which measures height in the atmosphere versus millibars. Remember I said how millibars is one way of measuring? You could convert that into pounds per square inch as well, but at ground level right here, it's actually a little bit over 1,000 millibars. But as you go up in the atmosphere, look what happens. It decreases very, very, very rapidly. And it gets very close to being zero as you go up towards the top of the atmosphere. So atmospheric pressure changes as you go up. But of course, we're not worried too much about vertical movement of air. We're actually more concerned with horizontal movement of air. So let's say, for example, that we have air. Let's see, I'm going to draw it on the bottom right here. We've got very dense air. All right, so air that is, all the molecules are very close together. They exert a lot of pressure. All right, a blob of air right there. We'll say right here is ground level. All right, and over here we have maybe some less dense air. All right, so there's less pressure. Now, of course, there's air in between, but think about it for a second. If you're in a hallway full of students, and the one side of the hallway is crammed full of people, very, very dense, and the other side of the hallway has less people, what's prone to happen? People tend to want to go from high density to low density, so that's going to be what happens. As air moves, as it moves from high to low pressure, we have what we call wind. All right. Now, again, I said that we don't care so much about vertical movement, but about horizontal movement of wind, or horizontal differences in pressure. Well, what would cause horizontal differences of pressure? Why would there be more pressure here than here? Well, because it's very closely related to temperature. All right. Temperature. Cold air is more dense. It's cold, and therefore the molecules are closer together. They're jittering less, and so they're closer together, which gives them more pressure. Warm air, the molecules are jittering more, and so there's more spacing between them, so there's less density, you might say, so there's less pressure. So air tends to want to move from high pressure to low pressure. I'll put an H right here and an L right here. And high pressure and low pressure areas generally correspond to cold air and warm air. So wherever we have a change in pressure or a difference in pressure, air is going to always want to move from high to low. Okay, but it's also true that temperature differences can cause air circulation around the world. Let's say that right here we have Earth's surface, all right, and we say right here is at the equator, all right. Now this is, that's the equator right there, and over here is, say, the North Pole. I'm kind of turning the world on its side, all right. So here's the equator, and over here on the far left is the North Pole. Well, at the equator, air is warmed. All right, air is warm at the equator. You know that it's pretty hot at the equator. So you've got air rising up because it's warm. Well, as you go up in the atmosphere, what happens? As you go up, I mean, mountain climbers will tell you, as you ascend through the atmosphere, it gets colder. And so the air that was previously warm at the equator, because the sun is always shining right there, that gets cold. That air gets cold. And it cools and it condenses. All right, you know that when air gets cold enough, we talked about in the previous section how cold air can hold less water vapor, and so when it cools to a certain temperature, it condenses. It rises, cools, and condenses. All right. Well, it's got to go somewhere when it rises up, and usually what happens is that it circulates towards the North and the South Pole. All right, so it can go that way, it can go the other way as well. Well, as you move towards the North Pole, what happens? Well, things tend to get colder right there. All right, and so this air cools down after it has gotten done condensing. And what does cold air do? Well, if warm air rises, cold air wants to sink. And so it's going to sink back down towards the Earth's surface. Well, when it sinks back down, you know that if you rise up, it gets cold. If it sinks back down, it gets warm. All right. Well, warm air can hold a lot more water vapor than cold air can. And so what's going to happen is it's going to not condense, but it's going to sink down and warm up and turn into a dry mass of air. So really the opposite thing happens as you move towards the equator as what happens at the poles. Towards the poles than as you move towards the equator, I should say. All right, equatorial air is warm and rises up and condenses. When it sinks back down, it warms up and it dries out. So this usually happens right here around 30 degrees north and south latitude. And so there are many deserts in that north and south latitude around the world. We're going to talk about this in more detail when we get into our atmospheric circulation diagram, and that'll be a different video. But this is just to kind of give you a little bit of background about how air circulates around Earth's surface. Okay, so I'm not going to repeat all that I just said right here, but this is going to be sort of a good little summary of what we're going to have in our circulation diagram. Air at the equator rises up, right, because it's heated. The equator is hot. As it moves towards the poles, this way and that way, it's going to cool down, and eventually cool air will sink down to Earth's surface. There, and where are we? Right here. Okay? It's sinking air. When that happens, you have, well, first of all, what happens when air rises up? We said it cools and condenses, right? So we've got clouds forming. So all along the equator right here, we're going to expect to see a lot of lush greenery, right? Because clouds are forming and water is falling in the form of precipitation. We're going to see that right at the equator. But on the other hand, when air sinks back down, it dries out. And so at about 30 degrees north latitude and 30 degrees south latitude, we're going to see great deserts because air is sinking. That's what happens when air rises up and when it sinks down. And it actually causes a lot of the landforms that we experience. So that's just a brief little summary of that. We'll talk more about that when we get into our air circulation diagram, but that'll be a different video. Okay, so one of the results of differences in pressure in the atmosphere are things called jet streams. Jet streams you can think of as being rivers of air that are up in the atmosphere. And what they do is they're high in the atmosphere towards the top of the troposphere or the tropopause. And what they do is they encircle the globe. They kind of wave back and forth. We say that they're westerly winds because they come from the west. We're not going to focus too much on wind names, but winds are generally named where they come from. So they come from the west towards the east, and they encircle the whole globe. And they wave back and forth due to the Coriolis effect. The Coriolis effect is a tendency of any kind of fluid moving in a straight line to want to bend off one direction or the other. So let's say air wants to move that way. The Coriolis effect will make it either spin that way or spin that way, depending on which hemisphere you are in. So we'll talk more about that a little bit later. But jet streams, what they do is they actually serve to direct weather systems or steer, you might say, steer weather systems around the world. In our hemisphere, the northern hemisphere, we have two jet streams. I'm not going to dwell on these too much. We've got a jet stream near the poles. We call it the polar jet stream. And we've got the subtropical jet stream. Sub means, and actually in this regard it means not quite. And so it's not quite tropical, so it's a little bit north of the tropics. And so right around where we are, we experience the subtropical jet stream, but there's one in the north that is much stronger and really drives polar storms around the North Pole. Again, we're not going to belabor that too much, but think of them as being rivers of air that encircle the world. All right, so think of them as being kind of like, see how it kind of waves back and forth? They don't swirl around the world in a straight line because the Coriolis effect is an effect that causes winds to kind of curve back and forth. More on that a little bit later. But we've got a polar jet stream, which is stronger, and a subtropical jet stream, which is less strong. But as you can see, the subtropical jet stream really moves right across our continent and steers a lot of the storms that we experience. Okay, well, what we are concerned with the most is, like I said before, air pressure differences horizontally. So let's say we have the ground right here, okay? And we have a high pressure area. I'm going to draw that in blue. Okay. High pressure. High pressure does what? Well, it wants to move air wants to move from high pressure, right? So it wants to move out of areas of high pressure. And we have a low pressure area over here. Okay? Low right there. Well, air wants to move into areas of low pressure. Air always wants to move from high to low. Okay, so here's what happens. We call these two different areas convergence and divergence. All right, right here we would call that a convergent area. Why? Well, because air is converging on this low pressure area. Air is all coming towards the center. And really it only has one place to go. The only place it can go if it converges from all directions, the only place it can go is up. All right? So all this air now is rising up. Similarly, or you might say conversely on the opposite, look at this high pressure right here. What's happening? Air is diverging from it. So we would call this a divergent area. All right, because air is, we'll just draw that like an air mass right there, okay? All right, air is moving out of it in all directions. So here's our convergent area, and here's our divergent area right there. By the way, what happens in between those areas? We get wind, right? Because air wants to move from high to low, W-I-N-D. That's what we experience as wind, air moving horizontally. So there's your house right there, okay? Why does wind move? Because there's a high pressure area over here, there's a low pressure area right there. Air is going to want to move out. Well, look at this now, all right? Now we've got air all rising up. It's all going the same place. And so at the top right here is where you would have high pressure. Why? Because all the air is going there. Likewise, why over here? Why is there high pressure air? Because air is coming from somewhere, sinking back down. Air wants to move out of low pressure areas into high. Air and air wants to move out of low pressure areas into high right here. So really what's happening is we have sort of like a 3D model going on where it shows us how circulation takes place. Air moves from high to low. This low air coming together causes high air pressure above that. This high air pressure moves out of the high into a low pressure area. And so since this is less pressure right here, there's only one place for it to go. It goes down and causes this high pressure area. So it's like a circulation pattern going on right there. I hope that makes sense. There's a lot of highs and lows going on right there. But what we have is sort of a 3D model. Maybe the next diagram will make a little bit more sense. All right, this looks really kind of scary looking, but look, at the ground right here, you've got a center of high pressure, and here you have a center of low pressure. Air moves out of an area of a center of high pressure. You would think it would just move out in all directions, right? Just move out like that, move out, move out. But what did I say causes air to bend off to one direction or the other? Well, that's a Coriolis effect. All right, so air wants to move out from high pressure. It actually swirls out in all directions. Likewise, air in low pressure area wants to shoot right into the center, right? But it doesn't just shoot straight into the center. It swirls into the center, all because of the Coriolis effect. Okay? Oh, ECT, sorry. This right here, this bending of the winds, and this bending of the wind right there is what's called the Coriolis effect. So, air moves out from a high pressure to low pressure. Where's the only place it can go? Only place it can go is up. All right, so it kind of swirls up like that. All this air is coming together right here, and I'm sorry, right here, coming together right here. So all that air that's rising up in that place becomes high pressure. Likewise, all the air that's leaving this place is leaving and sinking back down to create this high pressure area at the ground right there. So since it's leaving this area, we would say that area is low pressure. So I draw an L right there. So see how we have high to low, Air rising up, high to low, air sinking down, high to low, etc. These systems right here, high pressure and low pressure system, create the storms that we experience. And see how way at high altitudes we have this jet stream, this river of air? It tends to guide or steer these systems around Earth's surface. So we'll talk more about that in class, but hopefully this gives you a little bit of understanding into how air circulates around the world. And by the way, what did we say happens before when air rises up? It cools and condenses. That's why we have that cloud right there. So you can expect wherever you see a low pressure area, it's going to be precipitating or some sort of clouds or rain taking place. That's what you can expect from low pressure areas. By the way, this funny symbol right here, this blue and red thing, are front names or front symbols. They're showing that air is actually rising and precipitating right there. So I know that's kind of a lot all at once, but that's kind of our basic, you might say, our basic foundation for understanding high and low pressure systems. Well, like I said before, when air rises up, what happens? Oh, I don't want to draw that in red. Let's do that in black. What happens when air rises up? It cools and condenses. All right, so if you have air, maybe some warm air right here, an air mass, that is warmer than the surrounding air. So say the surrounding air right here is cold or colder. All right, what's going to happen? Well, this warm air is less dense. It's more buoyant, you might say, and so it wants to rise up. It wants to rise up in the atmosphere because the surrounding air is more dense. All right, so it wants to float, as it were, almost like a buoy. Okay, but when this air rises up, it doesn't stay the same temperature. What happens is it cools because as you go up in the atmosphere, it gets colder. And so this warm air, as it cools, it can't hold as much water vapor at colder temperatures, and so that water vapor starts to drop out and form clouds. Whenever you have air rising up, we call that unstable air. Now, when you think of somebody who's unstable, you think of them as, maybe freaking out on a moment's notice. But unstable simply just means prone to change. All right, so unstable air is going to change its, you might say, change its altitude or rise up or change its position. When air does that, when air rises up, it will cool and it will condense. So almost all unstable air results in some sort of precipitation. And we'll just leave it at that for now, all right? Actually, I will say one other thing. Let's say, for example, that you have some warm air. All right, and this can be a very dangerous situation. Some warm air right here that that cold air is coming over top of. All right, so here's cold air right here, and by the way, this bottom is just ground level right here. All right, so that's the ground, and you've got cold air over top of warm air. So this is all cold up here, and down below it's warm. Well, that's kind of that is a very unstable circumstance because this air wants to kind of flip-flop. Warm air wants to rise, cold air wants to sink, and when those air masses swirl around each other like that, and this warm air wants to rise up through the cold air, it can really be lay the groundwork for storms like tornadoes to take place. So this right here is definitely what we would call unstable warm air because it's underneath denser air. It wants to rise up through that air, and when it rises up, you can have a lot of energy released all at once. All right, and lastly, we're going to talk about fronts. Like I said, this was the fourth of our four main points of this section. What a front is a boundary between cold and warm air. A front is really a military term. It's a military term that kind of describes the boundary between two different armies. Well, you can think about warm air and cold air as being two different armies. And two different armies, they're different armies because there may be different peoples or different countries. They don't mix very well, all right? And so instead of the air just kind of swirling into each other, they don't mix, rather they push each other around. All right, so kind of like I drew before, we have, let's say, the ground level right here, and we have this blob of warm air sitting right here just sort of minding its own business. All right? Well, cold air comes in. And remember we said before that cold air has more pressure. It's denser, right? It throws its weight around a little bit more. These are like two armies right here. And when these two air masses come together and hit each other, you're going to have some sort of interaction. Since cold air is more dense, it wants to slide underneath the warm air. And in doing that, it causes that warm air to rise up in the atmosphere. You know what happens when air rises up, right? It cools and it condenses, and we have some sort of clouds of precipitation. But the way that these different air masses interact are called fronts. And we've got four of them that we're going to look at. Now, I'm not going to illustrate them in this video right here. There's going to be a separate video where we label the different kinds of fronts. And that'll be a separate diagram in a different video. But there's going to be four of them. We're going to talk about a cold front. We're going to talk about a warm front. I'm going to mention a stationary front and an occluded front. And all of these are indicated on a map by various different kinds of symbols. A cold front looks like a line with blue triangles. Well, they're usually blue, but that wasn't drawn very well, was it? I'll do it over here. A line with blue triangles on it. You can think of the triangles being kind of like icicles, all right? A warm front is usually red. It's a red line, and it has red semicircles on it. So it's kind of like little curves. All right. Again, I'll talk more about how these form when we get to that actual diagram. But a stationary front has reds on one side and blues on another, and an occluded front has them I'll say just kind of interspersed. So here's a stationary front, red and blue on one side of the other. An occluded front has them red, blue, etc. And what these lines are means it's the line between one air mass and another. So it's like the boundary line. All right, now you can read these descriptions right here, but when we get to the video where it talks about where we kind of label the different kinds of air masses, it'll make sense what these mean. But these are just simply lines on a map that show how different air masses, be they cold or warm, are interacting with each other. All right, so just real quick, see this cold air right here? Okay, this is kind of a 3D model, right? This cold air is moving in and then it's sinking underneath the warm air that's on the right-hand side. That warm air, it's almost like it's being boosted up in the air because there's like this ramp of cold air that's seeping underneath it. When it does that, it rises and cools and condenses, and we have big towering clouds that we call cumulonimbus clouds. All right, so right where those two air masses meet, see that right there on the ground? That's where you would draw your cold front line. That's the edge, the ground base, the leading edge between the one air mass and the other. On the other hand, this is a warm front. So right there is where the front line would be, and what's happening right here? Well, you've got cold air sitting over on the right-hand side, just kind of minding its own business. If warm air is moving rapidly, it's going to overtake that cold air, and it's not going to want to sink underneath it, right? Because warm air is less dense. It's prone to rise. But it's going to want to rise up over it like the cold air is a ramp. All right? And right where the warm air meets the cold air, that's where you would draw the line on the ground as well, or on a map. Okay, but as that warm air rises up, see it cools and it condenses as it rises up through the atmosphere. So that's going to cause some cloud formation and possibly some precipitation too. So these are the two main kinds of fronts. We'll talk about the other two when we get to the front diagram video, but that should do it for now. This last slide right kind of shows maybe a typical weather map where you would see all these, oh my goodness, what's going on with all these lines right here? Well, these green lines indicate areas of different pressure. You've got high and then stepping down into low pressure right here. But what we just talked about is these front lines. All right, so there's a cold front line right there. There's a warm front line. There's a stationary front line right there. And we don't have any occluded front. Oh, here we do. Here's an occluded front. Again, those are lines that show how air masses are interacting. And it'll make more sense when we do that video on that the front and air masses diagram. So that'll be a different video. For right now, I think you probably had enough. So that's section 4 in chapter 9. And for the time being, thanks for watching. I'll see you on the next one.